Okay, so hello everyone. Let some students in the class. Okay, so let's wait for some time, some 5 minutes, then we will be starting this session. Okay, so we'll start the session now. So first of all, let me introduce myself. My name is Himanshi Singh. I am currently a PhD scholar at Department of Mathematics, IIT Jodhpur. So I am currently pursuing the research in broad area of probability and statistics. And also I'm your TA for the course Essentials of Data Science with R Software 2, Sampling Theory and Linear Regression Analysis, which is taught by Professor Shalab on the SWAM portal. Okay, and we are basically having live sessions every week. So every week they are uploading the content for the this course, and I'm taking these live sessions every Monday. Okay, so basically this is our seventh live session. Okay, so this is the live session schedule. So basically we are having the live sessions every Monday. Okay, from 6 to 8 p.m. So this is our seventh live session, and we'll have in total 12 live sessions. Okay, and apart from this, these are some important links. So first one is the Google Meet link, which which is present there in the announcements, also on the NPTEL on the SWAM portal, and also it is present here. So you can access this live session using these links on the specified time. Okay, and the second one is the YouTube link. So it basically is the link to my channel on YouTube, where I'm uploading all the recording of these live sessions. Okay, the third one is the Google Drive link, where I'm uploading all the PowerPoint presentations and the R scripts, so you may access it from there. Okay, so all this material is there on YouTube. The live sessions video and the presentations are there on this folder. Okay, so basically, for our live sessions, the plan is that I give a brief recap about the topics which is covered in the previous week. Okay, and I'll just give you a brief recap about that, and then we'll just do some. If there are some examples which we can do to demonstrate those topics in R, then we can do that. Then after that, there are practice examples which is helpful for you to solve the assignments and all those things, and also it will be helpful to you in order to solve your final exam. Okay, and then I may take the doubts. If someone have doubt, then we can discuss that. Okay, so this was about the introduction, how this course is going and how we are conducting the live sessions. Okay. So now I think I will start the topics. So basically, in the last live sessions, in the last week also. So this today, we are basically considering the content of week 7 lectures. So basically we are studying about stratified random sampling. Okay, so what was stratified random sampling? I have just shown you here. In the previous session also we have discussed this. So this basically, this if you have n units of population, then from there we just construct different groups. For example, K groups, and each group will have some population. Okay, so N1 units are here, N2 units are here, and K units are here, and their sum is total N units. From those groups, we are taking samples. Okay, and then so this is basically the way to do the stratified random sampling. So if there is high variability in the data, so we just divide the data into groups such that uh, uh, among the groups there is heterogeneity, but inside a particular group there is homogeneity or less variability. Okay, then we collect the sample, and basis on that sample we just estimate the population mean and all those things we studied. So basically today I've included this here in order to discuss that whenever we are, so this is basically that capital N1 units, N2 units, and NK units, and from this N1 units we want to select a sample of small n1 units. Now how to know that what should be this small n1, n2, and nk? In order to draw a sample, we must know that what is the size of the sample we want to draw from the population. So how to know this small n1, small n2, and small nk? So basically, three methods were discussed in the lectures. So that is when we are considering equal allocation, and there is another method called proportional allocation, and there is a third method called Neyman or optimum allocation. Okay, so basically in equal allocation, the so if I have three groups, okay, from each group I will have same number of samples. For example, if this I'm drawing n1 sample from this group, n2 sample from this group, and n3 sample from this group, then all the threes are equal. Okay, and equal, and we basically know that summation of ni is kept this small n. Okay, and if all of them are equal, so this means 3 times n1 is equals to n, which implies that n1 is equals to n by 3. And in general, in place of 3, so this is a k3 stratum. So in general, we are considered k stratum, so it is n by k. So that's why here it is small n by k. So for equal allocation, we are getting the sample size. Each sample size from each stratum is small n by n, which is equal for all the stratums. Okay, so this is about the equal allocation. What about the proportional allocation? So basically, if there are more number of units in a particular stratum, then more sample we are drawing from that. So we are basically working on the proportional. So proportion. So basically, we are taking the sample size of Ni, which is proportional to capital Ni. That is the size of the stratum. Okay, so that is small ni is proportional to capital Ni, and where we got the constant of proportionality to be small n by capital N. Hence, we got this small ni to be small n by capital N and capital Ni for all I going from 1 to k. So this is for the proportional allocation. So we can find these values n1, n2, nk for each I. Okay, here also and here also. Apart from this, in order to also taking into account the variability in the stratums, there is a Neyman or optimum allocation. So if there is large, so for example in this first group the variability is large as compared to second, so the more number of sample will be taken from these groups in order to decrease the variability. Okay, so here we are basically considering both the things. We are considering proportion thing, and we are also considering the variability. So here both the things are considered. Okay, and on the basis of that, this condition was obtained that Ni is directly proportional to capital Ni into capital Si. So Si is the standard deviation. So this is basically the measure of the variability, and capital Ni is the size of the stratum. Okay, so a small ni is proportional to the product of both of them, which basically gives us this. So small ni is equals to small n ni divided by the summation of ni si. So this will be basically the size of the sample size whenever we are considering this optimum allocation method. So these are three methods, where first method is giving nothing towards the proportion and nothing towards the variability. However, the second one is giving a little weightage to the proportion, that okay, we are taking proportion into account and we are saying that small ni is proportional to capital Ni. However, the third method is giving importance to the proportion as well as to the variability. Okay, so that's why this method considered to be more optimized as compared to the other ones. However, for this method, we have to know the SIs, basically the standard deviation for the this stratums, the whatever the capital Y1, x1, x2, x capital N1. We have to know all the values of all the elements in the population. So that's why that is a drawback for this. However, we can estimate SI, okay, and we can use that estimate in order to find out the sample size. Okay, so in general, we have these three formulas for allocations of the sample sizes for the different stratums. Okay, now these are the sample sizes. Now what about the variances under those allocations? So whenever we were considering about the stratified random sampling, so in order to estimate the population mean, okay, so there was a estimator, that was the stratified mean y bar st. That was nothing but wi. So that was wi into y bar, I going from 1 to k, yi bar. So this was that thing, y bar stratified. So that was the stratified mean, which was basically the estimator of population mean. Now, what will be its variance? So we discussed under simple random sampling without replacement. It was like summation I going from 1 to k ni minus ni divided by ni wi square si square. So we are basically considering the variance here, and then we are taking out wi outside, and we are finding out variance of yi bar. However, if we are considering variance, this variance under the wherever the sample sizes are decided by the proportional method, proportional allocation method, then we basically put the values of ni, so which was basically what n divided by n into ni. We'll put this value here in this expression, and we can find out this expression. So this is for the variance of y bar stratified under proportional allocation, and similarly this is variance of y bar stratified under optimal allocation. Okay, so these are the expression which can be simplified only by replacing the value of small ni by this expression for the proportional, and for the optimum allocation by this expression. If we replace, then we will get these expressions. Okay. However, if we consider only y bar, not the y bar stratified, then variance under SRS WOR is n minus n divided by n s square. This already we have discussed in the previous lectures. And there is also one inequality which follows that if the ni's, the stratum sizes and capital N are large enough, such that capital Ni minus 1 upon Ni, this is approximately 1, and similarly this is approximately 1, then the variance, the inequality in the variance lies in this way. So the variance of y bar under SRSWR is the highest, and then the variance of the proportion, the variance under the proportional allocation of the y bar stratified, and then the variance, the variance of optimum allocation of variance of y bar under optimum allocation is the least. So this is intuitively, this is also true, because in y bar stratified, in the optimal allocation, we are taking into account both the things, the proportion as well as the variability of the data. Okay, so both the things are taken care of. That's why the variance of the final estimator is coming out to be less. Okay. However, there are some drawbacks in variance of this y bar stratified, or in fact the y bar, if we are considering the optimum allocation in Ni, there is a drawback that Si may not be known always. Okay. However, it can be estimated. Okay, but intuitively it is clear that variance of under optimum allocation, the variance of y bar stratified is least, because we have taken care of both variability as well as the proportional. Fine. So this was about the variances. Now, if I want to draw a sample through the stratified random sampling, then there is this command stratified and this one. So this basically is in the lectures also it was told, and there is a function which is available on a particular site, which was given there in the your lecture notes also. So from there you can get this function. So this is basically this function, this which I have included in R script also. This is stratified function. So this basically is the function which you must have in your R, then only you will be able to run this stratified function here, which is given here, in order to generate the stratified sample from the data. Okay, so here the command stratified is used basically. So in the first argument, the data, whatever the data you have, so it should be in the format of data frame. So it should be data frame. It can be data frame, or it can be data.table format. Okay, or it can be a matrix. Okay, so these three formats are allowed. So here we just input the data, whatever data we want to draw a sample from. Then in the second one, we have to specify the name of that group or the column which is present in the data frame, which we want to group into. So for example, there is a group, there is a column A, for example, in which there are three types of things, like there are numbers like 25, there are numbers 75, there are number of 95. Only three numbers are there. Repeatedly, they are like there are 525s and 775s and 1095s, for example. So we can group this A into three. We can group this in A into three groups. Like one is when the value of A is 25, another is when the value is 75, and third one is whenever the value is 95. So that column we should specify here, which we want to group into. Okay, then size. So size, basically size can have three type of argument. So if we specify size to be decimal between 0 and 1, so that basically imply that we are taking the allocations to be proportional, the sample allocations to be proportional. So for example, if I take this size to be 0.2, so that implies that 20% of each of the, so 20% of so for example, if capital N1 is 300, then 20% of the sample will be 20% of the data will be in the sample, 20% of 300. Okay, and if capital N2 is 200, then 20% of 200 will be there in the sample. If this is in the population, the size of the stratum, so it is 20% of 200 will be there in the sample. And similarly, if there are more than like 2 stratums, for example, there are 5 stratums, and from each of the stratum, 20% of the data will be there in the sample. Okay, if we have this size to be decimal. If the size is a positive integer, then it will give us the same number of observation from each group. So if I give size to be 10, then from each group, it will give me samples of size 10 from each group. Okay, and if it is a named vector, that then it will imply that the function will check whether the length of the vector matches the number of groups and that the names match the group names. Then it will give us the names also. If it is a named vector, then it will basically compare the two characters. For example, in double quotes we write, so it will compare basically if you write that in size. Fine. Now, again, if there is a data in, for example, you sampled it and you find out the sample, and if you want to um, particularly take a particular row, particular column, or a particular element from that data frame, so that will again be a data frame, and then you can take it by using the dollar sign that we have done previously in our first class. So basically, let me show you. So if for this, first of all, I have to call the library sampling. Okay, then I will run this function. So you may get it. I will upload these slides also. So these are script also. So you may get this function from there also. And sir has also given you a link from which you can get it. Okay, so I have run this stratified function. Then I have created a data frame df. So let us see what this data frame is. Okay, so let me show you what this data frame is. So this data frame is like this. So here we have this ID, we have A, B, C, D, E columns, and on A columns we have Lucknow, Mumbai, Kolkata, Kanpur, Delhi, these kind of groups. Okay, and in B we have these numbers, C also we have these numbers, D we have three numbers 50, 95, 75, and they are repeatedly there in these column, and in E we have the gender, male or female. Okay, so here we have this data frame. Now if I use this command stratified df, so at the first argument I have given the data frame. In the second argument I can give any of this column names. Okay, so here I have given A, and in the last argument I have given 2. So this basically say that from each of the group 2 sample will be taken. Okay, so if I run it, so here I got this. So here you can see it said that A is basically grouped. So if you see A, so A is divided into how many categories? So there is Lucknow, Kanpur, Mumbai, Kolkata, Delhi. So there are 5 different you can say groups can be made of. One is for Delhi, one is for Kanpur, one is for Kolkata, Lucknow, and Mumbai. And since we have specified here 2, so 2 samples are taken from each of the groups. Okay, and other things are there with it. Okay, so here you can see stratums. How many stratums are there? 1, 2, 3, 4, 5 stratums are there, because we can divide this the column A into 5 groups. Okay, and apart from this A, if I write B, if I write B here, then you can see there is an error. So why this error occurs? Because at the last I have written 2. So here actually the this B column, you can see that the numbers are like 101, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there is no matching here. So this cannot be divided into group of size 2. So here the it can be divided only to the group of size in particular group there is only one element, because no same elements are there. So there will be 50 groups if I do it here. So if there are 50 groups, each consist of one unit, then how can I have a sample of size 2? So that's why if I write it here 1, then I'll get the output. So in the output, what I got all the 50 values, and I got the same data frame. And here you can see the stratum. So how many stratums are there? 50 stratums are there, because there are 50 groups. Because we cannot divide it into groups where one group have two elements, because there is no similarity. These are two different numbers, so it has not divided it into it has divided into 50 groups only. Same thing if I do with D. So for example, if in place of A I write D, so you can see in D there are only three numbers which are repeatedly occurring, so that is 50, 75 and 95. So it can be divided into three groups. Okay, so if I do it with D, then you can see here I got the answer. So here I got two samples from each of the group. There we had three groups, and from each of the group we got two samples. Okay, in place of 2, if I write 0.2, for example, so it will give 20% of the sample from that. So if there is 100 elements in the data, then it will give me 20 points from it, because it will give me 20% of the data. Okay, so if I run it, so you can see here I got four samples from the data where there was 50, and five samples from the data where there was 75, and three samples from the data where there was 95. Okay, so this is the way by which we can get these outputs. Okay, now here you can whenever we are considering, so we are getting 20% of the data from the particular population, okay, or a particular stratum. And whenever we are writing a whole number, for example 2 or 1, then we are getting a so if I write 2 here, so that implies I will get two sample from each of the group. Okay, what if I want that from group 1 I want two samples, from group 2 I want three samples, from group 3 I want five samples. So what if that condition holds? Then what if I want to draw a sample in such a way? So for that we also have another command. So in the next slide we can see, so this command strata. So basically we use this function strata. Okay, so where at the first argument we give the data, at the second argument we give the strata names. So basically strata names is equals to those names of the columns for which we want to create groups. Okay, and the third argument, this is size. So it takes a vector. So I have not written the value, numerical value, but here size is equals to C, where you can specify the number of sample size you want from a particular group. Okay, and method is equals to SRSWR. You can also use SRSWR. Okay, so here also, if I can show this to you, here I have written this code. So here I have taken strata, and from not data strata, if I take TF only, the same data frame I'm taking. So I've given the data, and then the strata names I have taken the, okay, just forget this. I will consider this one. Okay, so strata, and at the first argument I given this data frame. At the second, the strata name I have given D, means the dth column, D column. So this column, this one. So we can see this can be divided into three groups. Okay. However, it can be divided into three groups, but we want that the first group, three samples should come. From the second group, five samples should come. And from the third group, four samples should come. So that's why I have given size to be 3, 5, and 4. And then I have specified the method to be the without replacement, simple random sampling without replacement. Then if I run it, then you can see here I got this str to be. So here you can see that D is displayed here, and only D is displayed. Okay, and but the other columns like A, B, and all those columns are not displayed. Only D is displayed, but the sizes are according to us: 3 for the 50, and 5 for the 95, and 4 for the 75 thing. So we got the desired size of the sample. Sample size, we want these sample sizes, so we got this by using this command. So these are the two different ways by which we can get the stratified samples directly. Okay. Now, apart from this, there is also a terminology called empirical distribution function. So this is a different thing. So basically, this stratified thing, stratified random sampling, we are done with. And when we talk about the empirical distribution function, so basically, if I do not have the knowledge of the whole distribution of the whole population, so for example, x1, x2, xn, this is the whole population, and I do not have the information that what is the distribution function for this population. Okay, however, I have a sample, for example, x2, x1, x1, x2, and xn. I have this sample. Now, from this sample, how can I get this idea that what may be the distribution of this population? So basically, this empirical distribution function, this it approximates the cumulative distribution function. So we basically, whenever we talk about the probability distribution functions or cumulative distribution function, it basically tell us about that how the probability over the whole support is defined. Okay, so if you know the cumulative distribution function for a particular random variable, you know everything about this random variable. You can find out all the probabilities for every set under it. Okay, so now if I want to know the CDF and I do not know the CDF of the population, then I can estimate using the empirical distribution function. So basically what this empirical distribution function do, it assigns the equal probability to each of the outcomes. So for example, x1, x2, xn is the sample. So it will give 1 by n probability to each of the sample. So basically it will give you that probability x1 is equals to so probability that the probability that x1 is equals to x1 is 1 by n. Okay, and so if the x1 appears, then it has the probability 1 by n. Similarly to other samples. So for example, x1 is appears to be, so this is the realized sample. So for example, the population is like 1, 2, 3, 4. If this was the population and the sample is drawn. Okay, so sample is drawn where x1 is 1, x2 is again, x2 is 2, and you let it to be 3. x1, x2, x3 to be the sample, and this is 4, for example. So it will give 1 by 3 probability to 1, it will give again 1 by 3 probability to 2, it will give 1 by 3 probability to 4. So what basically it means, now what will be the total probability according to this empirical distribution function? So it is like probability x is equals to 1 will be 1 by 3 because this has given 1 by 3 probability to 1. Okay, probability that x is equals to 2 will again be 1 by 3 because it has given 1 by 3 probability to 2. Probability that x is equals to 4 is again 1 by 3. But apart from this, like probability, now x can be, since in the population 4 is also, sorry, 3 is also there. So what will be the probability x is equals to 3? So that will be 0 according to this sample. Because we are basically constructing the empirical distribution function from the sample and we do not know about the population. So apart from the values present in the sample, if there is something, so we'll give the 0 probability to all those things and we'll give equal probability to the points which are present in the sample. Okay. Now in place of this, if it happens like x1 is 1 and x2 is again 1 and x3 is 4, if such kind of thing is happening, so that implies that 1 is so it is giving 1 by 3 probability to 1 and again 1 by 3 probability to 1. So basically it is giving 2 by 3 probability to 1. So then in that case, probability of x is equals to 1 will be 2 by 3. Okay, probability of x is equals to 4 will be 1 by 3. And apart from that, probability x is equals to 3 and probability x is equals to 2, both will be 0 because they are not there in the sample if we consider this situation 1, 1, 4. So this is the way the empirical distribution function works. Okay, and if I have an parameter which basically depends upon the distribution function, cumulative distribution function f, and I want to estimate it, then I can just plug in the empirical distribution function into it, and it will be the plug-in estimate for that parameter. Okay, so the main thing about the empirical distribution function is that it gives equal probabilities to the values which are there in the sample, and apart from the sample, if there is some value in the population which is not appeared in the sample, that value will get 0 probability. Okay, so this was about the empirical distribution function. Now there is a bootstrap methodology. So whenever we do not know the whole population, and I want, so for example, I want to estimate a parameter theta, and theta hat is the estimate. So by theta hat, we will estimate theta. Okay, now in order to know the properties of theta hat, we get a condition like we want to estimate, we want to know that what is the variance of theta hat. Now, if the variance of theta hat is directly not, we are not able to simplify that what is the variance, we are not able to calculate it easily, then for those scenarios, this bootstrap methodology basically is used. Okay, so how it is used? So if I have a sample, sorry, if I have a population x1, x2, xn, okay, and a theta hat is an estimator of a theta parameter theta. So it's not always easy to find out the variance, as I have already stated that it is not always possible to find out the variance of the theta hat. Okay, so what we do, so for example, we do not know the population, but we are assuming that we have a particular sample with us. Okay, now from that sample, what we can conclude about using the bootstrap methodology, what we can conclude about the variance of the estimator. Now, if theta hat is an estimator, so basically it is a function of a sample only. Okay, now if I have a sample available to me, I1, I2 till In. So what I will do, I will again resample this. So I will again draw a sample of size n from this sample. So now I'm considering this as my population, this sample as my population, and I'm drawing a sample from this population. So I am drawing a sample of same size from this population. So that is, I'm just taking it to be x11 till x1n. So 1 is showing that this is my first bootstrap sample. Okay, and it is of size n, the same size. Okay, then again I will draw a sample which is x21, x2n, which will be the second bootstrap sample. Similarly, I will take, or I will generate b bootstrap samples. So this will be the bth bootstrap sample. So that is xb1 till xbn. So now I have b samples. Okay, I have x1 star, this is a sample, x2 star, this is again a sample, and I have xb star. So I have b samples with me. Now what I will do, I had this estimated theta hat. Okay, now for each of the sample, I will find out the theta hat. So that is theta hat x1 star. Then I will find out theta hat x2 star. Then I'll find out theta hat xb star. So for each of the sample, now I find out the estimate. So what is the estimate coming from these samples? Okay, then the mean of these estimates. So I found out these estimates, and if I find out the mean of these estimates, so that will be theta hat bar. Okay, so that will be an estimate for theta hat. Okay, so that will work as an estimate of theta hat. So it is an estimate of theta hat. Okay, but we want what is the variance of theta hat. How can we approximate the variance of theta hat? So basically, I will find out the variance of these quantities. So uh, I have this theta hat x1 star. So this is a particular quantity. I will get a particular number. So basically, I have this sample. So these will be numbers. This will be a function. I'll put those numbers into this function, and I'll get a particular value. So I'll get b values. Now from those b values, I will just find out the variance of those. So I had this theta hat. So theta hat x1 star I have till theta hat xb star I have. So I have this b values. Okay. So it is like y1, y2 up till yb kind of thing. So I will find out yi minus y bar whole square summation 1 upon n minus 1 kind of thing, which we used to find out before. So now I have b value. So I'll find out 1 upon b minus 1 summation b going from 1 to b theta hat xb star, that is a particular value, and we are subtracting their mean from it and we are squaring it. So that was same thing like this. So basically we are finding out the variance. So this variance, if the small n and this capital B, so if the size of the bootstrap, so the number of the bootstrap samples are very high and the size of the sample is also large, then we can say that this variance of theta hat, this VB, this approximate the variance of theta hat. Okay, and also the bootstrap estimate for the standard error of theta hat will be square root of this quantity. Okay, so this way, through the bootstrapping, we can find out an estimate for the variance of the estimator. Okay, so this was about the bootstrap thing. We will do a question on it also, then it will become more clear to you. Okay, so now we'll start with questions. So okay, so is it clear now? Can I move forward towards the questions? Actually, I have not shared the screen when I was showing this R script to you, but it may not be. It was not visible actually to you, and okay, so here I have given this whenever I was talking about this how to draw a sample, stratified random sampling, then this function I have given here, and I have defined the data frames, and I have shown the output here. So this basically was the same thing which sir has taught in the class. So I will give you these R scripts, so you can just run it and you can find out that how to draw a sample. So this was the function. This was the main function. Okay. So my screen was not shared. That's why the R script was not visible. So if there is some doubt, then you may ask. Otherwise, I will start with the questions. Okay. So if there is no doubt, then let me start with the questions. So a population is divided into 4 strata. So there is a population of size n. So it is divided into 4 strata. Okay, S1, S2, S3, and S4. A total sample of size 80 is to be selected using equal allocation. So basically from it, a sample should be taken, a sample should be taken, a sample should be taken from each 4 of them, such as the size is 80. Okay, so this is basically N1, this is N2, N3, and N4. This should be 80. And where we are using the method to be equal allocation. Equal allocation means that we want equal number of samples from each of these stratum. Okay, so we can directly say that there are 4 stratums and total is 80. So 80 by 4, we can find out that NIs are 20. Okay, so what NI is basically, it is n by k. So here n is 80 and k is 4. So this is 20. So n1 is equals to n2 is equals to n3 is equals to n4 is equals to 20. So this is a pretty simple thing where we are considering the allocation to be equal allocation. We want equal number of samples, and we note that total sample size is 80, and we can find out directly that from each stratum we want to collect how much of the sample, the units of the sample. Okay, so this was easy. So is it fine? Is it fine? Any doubt in this? Okay, so we'll move then for the next question. So now our population has three strata with the following sizes. So we have this three strata and the population sizes are 200, 300 and 500. I want to draw a sample. So basically I have N1. So this is N1. This is N2. This is N3. Okay. And the total sample size small n is 100 and capital N is, so capital N is, I can see that the sum of these, so which is 1000. So capital N is 1000. Total sample size I want to draw, small n is 100. Okay. Find the sample sizes using proportional allocation method. So I want N1, I want N2, I want N3. So for the proportional allocation, we have the formula that Ni is equals to small n by capital N, capital Ni. Okay, so N1 will be, so N is 100, capital N is 1000, and this capital Ni is 200. Okay, so N2 will be 100 divided by 1000 into, so what is capital N2? It is 300. And N3 is 100 divided by 1000 into 500. So this comes out to be 20, this comes out to be 30, this comes out to be 50. So basically we should have 20 samples from the first stratum, 30 samples from the second one, and 50 samples from the third one. Okay, you can see that here we are having this quantity same for all the sample sizes. Okay. You can also say that this is nothing but 10% of the data is coming. So 10% of the sample we are taken from each of the population. So in the code also we can construct this data frame, and we can, in place of size, we can write 0.1. So then it will give me 20 samples from the first one, 30 from the second, and 50 from the third stratum. Is it fine? Is it fine? We are just using the formula, nothing else. Okay, so let's see the next one. So a population has 5 strata with equal variability. So basically we have this population, okay, of size n. Now it is grouped into 5 stratas. Okay, this one. Now the variability is same. And how variability is measured? It is measured in the form of SI. So that implies this S1. Here the variability is S2. Here the variability is S3. Here S4, S5. Okay. Another question, it is saying that these SIs are equal. So the variability is equal. So S1, S2, S3, S4, S5 are equal. Okay. Now it is saying the total population size is 1000. So this is 1000. I want a sample of size 100. So basically if I take the summation of ni's are 100. So basically the summation of ni's is 100, which is small n, nothing but I is equals to 1 to 5. There are 5 status. Fine. Now, which allocation method would give the same result as proportional allocation? So first of all, let us see what proportional allocation will be. So proportional allocation will be, so for proportional allocation method will give us Ni to be small n by capital N into Ni. So this is the proportional allocation method. Now, what is the equal allocation? So for equal allocation, Ni is nothing but n by k for all I. But they are not equal, because here it is n by capital N into Ni, here it is n by k. So they are completely different. So they are not different. They are not same. So equal allocation will never give us the proportional allocation, the same result as proportional allocation. Let us see about the Neyman location or the optimum location. So for the Neyman allocation, what we have? We have Ni to be equals to n into capital Ni into small, Si divided by summation of Ni into Si. I going from 1 to k for all I is equals to 1 till k. Here the k is 5, no problem. Okay, now we know that each Si are equal. We know that S1 is equals to S2 is equals to S5. So all are equal. So k is 5 here. Okay. So since all are equal, so we can take that. So this is equals to let A. This is equals to let this to be A. Okay. So then Ni will be what? N into Ni A divided by summation of Ni into A. I going from 1 to k. Now A is a constant, so we can take it out. So it is N into Ni A divided by A summation of Ni. Okay. Now this A got cancelled and the summation of Ni is nothing but the capital N. So it is Ni is equals to N by capital N into Ni, which is nothing but the proportional allocation. So which shows that the Neyman allocation under the assumption that the variability is same gives the proportional allocation. Okay. So this Neyman allocation is correct. So both A and B is not correct, none is not correct. So Neyman allocation will give us the same result as proportional allocation whenever the variability in the stratas are same. Okay, is it clear? Okay, then we'll move for the next question. Yeah. So this is that a population has 3 strata with the following information. So we have these 3 strata where the Ni, NH or Ni are given, and here you can write Ni also, NISI, because we are giving us those terminologies or the notations. Okay, so we have these NIs and SIs. Total sample is given. Total sample size is 60. Okay, now I want sample sizes using Neyman allocation. So we will just use the formulas. So for the Neyman allocation, so this is N1, N2, N3 and S1, S2, S3. We have small n to be 60 and capital N to be 300 plus 200 plus 100. So it is 600. Okay, so now what is for Neyman allocation? Ni is small n NISI divided by summation of NISI. So the summation of NISI is common to all. So let us find out first that. So NISI here it is 200. So this is NISI. So this is 200. This is 800. This is 1800. Okay. And its sum is 2800. Okay. Now, what is N1? So N1 is equals to N into N1 S1 divided by the summation of NISI. This is 2800. Which is equals to small n is what? 60. N1 is 100. S1 is 2. So this get cancelled. This also got cancelled. So it is 30 by 7. This is 4.2, so which is approximately 4. Okay. What about N2? So N2S2 divided by 2800. So this is 60. What is N2? 204. So it is 200 and this is 4 divided by 2800. So this is 14. So this is 120 by 7. This one. Let me use R for this. So this is 120 by 7. 17.14. So if there is some mistake, then you just tell me if there is some calculation mistake. I hope it is correct. So it is 2800 and this is Ni 200 into 4 into small n, which is 60. So this got cancelled. 14 to 20 by 7. I think it's correct. Now what about N3? So N3 is small n is 60. Capital N3 is 300 and S3 is 6. Ninety by 7. So 90 by 7. That comes out to be 12.85. So which is approximately 13. So I hope the calculation is correct. Just cross check it. Is the formula correct? Is this calculation correct? Because if I We check it once. So it is 60 into 100 into 2 plus 60 into 200 into 4 plus 60 into 300 into 6. 60 into 300 into 6 divided by 2800. So it is 200, 800, 1800. Divided by 2800. So the sum should be 60. What is the mistake then? So okay, let me calculate it again. So n1 will be small n 60. Capital Ni is 100 into 2, that is 200 divided by 2800. Okay, and this n2 will be 60 into 3, 200 into 4 divided by 2800. Yeah. So it comes out to be, so 60 into 200, so it is like 60 into, so it comes out to be 4, approximately 4, and one, yeah, so it comes out to be 60 into 200 into 4 divided by 2800. So it comes out to be 17.14. It is 4.2 something. And the third one is 60 into 300 into 6. Yeah, so third one, there is a mistake in the third one actually. So this is, wait. So because the sum should be 60, the sum of n1, n2, n3 should be 60 because we have this sample size to be 60. So it is 300 into 6 actually. So it is 60 into 300 into 6 divided by 2800. So what it will be, this will get cancelled. And this 6 to 3, 14 times, and this 2, it is 3 3s and 9, 2, yeah, so there was 270 by 7. So that is 38.57. So yeah. So this is 38.57, which is approximately 39. Okay, so there was a mistake in this calculation because the sum should be actually 60. So here we are getting this to be 17, this to be 4. So 17 plus 4 plus 39. So that should be 60 because we should have this sample size to be 60. Now it's fine. So there was a mistake here. I hope it's clear. I hope this question is clear. Is this question clear?
Yes, ma'am.
Okay. Okay, so then we'll move forward. So there was a little mistake in this. Only we are just using the formula, nothing else. Okay, so we'll move forward. So the question says that which of the following statements is true? So equal allocation minimizes variance in all situations. So for example, I have a stratum. Yeah. So for example, I have a population from which the it's not working now. Just give me a minute. Okay, so if I have this population, okay, and I'm dividing it into different stratums and by equal allocation. So equal allocation means, so here this is stratums and I'm taking the sample using equal allocation. Now in the equal allocation thing, I'm taking, so if it contains, for example, 100 samples and it contains, so not 100 samples, 100 in the 100 units, and if it contains 20 units, if it contains 1000 units, and this contains, for example, 10 units, okay, and the total population is the sum of these. Now, if I take equal sample from each of them, then we have not even taken care of the proportion, and we have not even taken care of the variability also. So both the things, in the situation of the equal allocation, neither the proportion and nor the variability of the population is taken care of. So that's why equal allocation does not minimizes the variances. It basically, so it will have the maximum variance if I have to choose between the equal allocation, proportional allocation, or the third one, the optimal allocation. Okay, so is this equal allocation minimizes the variance in non in all situation? No, so it does not minimizes it. So what minimizes it? Basically, so if I choose the optimum allocation, there there is a certain criteria over the variance, because there we are taking about that small ni is directly proportional to nisi. Variability is coming into picture in that methodology only when we are considering the optimum allocation. Okay, if you are considering proportional allocation also, then also there is nothing about the variability of the data. So we are not, the variability is not taken care of there also, there only proportion is taken care of. However, in equal allocation, equal number of samples are taken from each of these stratums, so the variance will not be minimized. Okay, now proportional allocation gives the same sampling fraction in each stratum. So what does sampling fraction means basically? So what sampling fraction is? So sampling fraction is Ni, sorry, capital Ni, not capital Ni, small ni by capital Ni. Okay, so this is the base, this is the sampling fraction actually. Okay, so does proportional allocation gives the same sampling fraction? So let us see. So let us see that. So let me take a page. Okay, so here let us talk about the proportional allocation. So in the proportional allocation, we have Ni to be equals to small n by capital N into capital of Ni. Okay, so for all I we have this, for all I until k. Now if I take this Ni here, so Ni divided by capital Ni is equals to n by n for all I going from 1 to k. So for all these stratums, this sampling fraction is nothing but this ratio, this small n by capital M, which is same for all stratums. Okay, so it is not varying depending upon the stratum. So the sample sizes are varying, but if I consider about the fraction, the sampling fraction, this is same. Which is basically the sampling fraction is nothing but how the percentage of the data. So it is the percentage that what is the proportion of this particular data according to the size of the population or particular population of the stratum, that is capital Ni. So that is basically the same for all these stratums. Okay. Now the next one is Neyman allocation ignores stratum variability. So what Neyman allocation does, that Ni is directly proportional to NiSi, which was it was taking into account the variability thing. So it is saying that Neyman allocation ignores the stratum variability. So no, it is false. So it is true. This is false. Okay, now next one is equal allocation depends on stratum size. So what equal allocation was? In equal allocation, we are saying Ni is equals to n by k for all I, going from 1 till k. So does it depend on the stratum size? What stratum size is? Capital Ni. So this is the stratum size. So does it depend on the stratum size? No. So it is also false. Is it fine? This true false?
Yes, ma'am.
Okay. So now the next question. So basically here we are, the question says that the population is divided into 3 strata. A total population size is 1000. Sample of size 90 should be selected. So I want a sample of size 90. Okay. The total sample size is 90. Okay, now I want to select the samples using equal, proportional and Neyman allocation. So all the 3 methods I want to select the sample sizes. Okay, so basically I want, for equal allocation, I want n1, n2, n3. Okay, let me write it as E in above it in order to differentiate. And for proportional allocation, I want n1, n2 and n3. Let me write P above it in order to show that it is uh, because of the proportional allocation. And for the Neyman allocation, I want n1. O, I will write O for optimal because n and n will be same. That's why n3. Okay. Now, find the variance of the stratified sample mean for all the 3 cases when sampling is done by SRSWOR. Okay, so I want the variance of the stratified sample mean. So first of all, the variance of Y bar ST is what? So it is Ni, not, it was summation I going from 1 to k, okay, Wi square Ni minus Ni divided by Ni into Ni to Si square. This was the formula for it. Okay, so it is whenever we are considering the without replacement thing. So this was the formula for that. Okay, now we know the capital Ni's. Capital Ni's are with us. This is 200, 300 and 500. Okay, so what is the small Ni's? Small Ni's are not given here. So basically for different allocation methods, we have to calculate the Ni's first. Then we will replace the Ni's here and find out the values. SI squares are given. SI squares are given here. Okay. So basically here, first of all, what is WI? What WI is? So WI is small ni by capital Ni. Okay. We have defined it here. Oh, not capital Ni by capital N, sorry. So it is the proportion of the stratum size to the total population. So this is WI. Okay, so first of all, we will calculate the WIs because it will be same for all the allocation methods. So W1, W2 and W3. So what they are? So capital N1 is 200. Let it be Ni and Si. So it is 200 by 1000. So it is 0.2. Similarly, it will be 0.3 and it will be 0.5. Fine. Capital NIs we have 200, 200, 300 and 500. Now small NIs. Now small NIs based on first of all the equal allocation we talk about. So N1O E equal allocation and N2E and N3E. Now for equal allocation they are same. Okay, and what it is N by K. And what n small n is? Small n is 90 and K is 3. So it will be 90 by 3. So N1E is equals to N2E is equals to N3E. It will be 30. Fine. Now what will be for the optimal, sorry, for the proportional allocation? So N1P is equals to, for the proportional allocation what we have? N1 by N1 into, not N1 by N1, to capital N, I think. So it was N by N to N, sorry. So it is N by N into N I. And I, here we are talking about 1, so it will be 1. Okay, so what is a small n by capital N for it? So first of all, let me calculate that here only. Small n by capital N is 90 by 1000. So it is 0.09. So it is 0.09 into N1, capital N1. So that is 200. Okay, N2P will be 0.09 into 300. N3P will be 0.09 into 500. So it will be 18, it will be 27, okay, and it will be 45. Okay, so this will be the sizes when we have proportional allocation. Let us talk about the optimal allocation. So that formula is n into n1s1 divided by summation of NISI. So let us first calculate the summation of NISI. So it is SI square. So what will be SI here? So it is 4, this is 5, this is 6. Okay. So it is 800, this is 1500, this is 3000. So it is, I hope I'm correct, 800, 1500, 3000, and this is 8, 9, 10, 11. Yeah, 5300. So it is small n is 90, capital N1 S1, 200 into 4, that is 800, divided by 5300. Okay, and here 90 into this NISI is 1500, 1500 divided by 5300. Again, I have 90 into 3000, 5300. So these got cancelled. So now what will be the value? 90 into 8 by 53. So this is 13.58, which is approximately 14. Okay, 19 to 15 is 25.47. Okay, and 19 to 3, 5 point, not 3, it is 30. 50.9434. So this is approximately 51. This is approximately 25. Okay. So we have to make them such a way so that we have total size to be 90. Okay. So this is 459 plus 110, 5, 6, 7, 8, 9. So that it is 90. So these are the sizes for the optimal allocations. Fine. Now we got all the quantities. Okay, we have W1, W2, W3, we have capital Ni, small ni's accordingly. So now we will find out. So we will find out now under equal allocation. We find out the variance of y bar. So variance of y bar st will be. So for that, let me write it E here. Okay, so that is summation of Wi square means we'll square this one. So 0.2 square and then capital N1. So capital N1 is 200 minus small n1 when we are taking the equal allocation. So what was it? N1E. So that was 30. So that is 30. 200 minus 30 divided by n1 into n1 s1 square. So I have written 300 is 30. Now 200 into 30 and multiplied by s1 square. So s1 square is 16 plus again the second one, the second term. So it is 0.3. So 0.3 square into 300 was the size minus 30 divided by 300 into 30 multiplied by, okay, I'll write it in the next page. So this is 300 into 30 multiplied by this 5, not 5, 25. So the calculation is gone. So let me see it again then. So it is 25.47. So that was approximately 25. No, so it is 13.58. Fine. So now we have so yeah, we have capital N1 to be 300 minus 30 divided by 300 into 30 multiplied by 5, I guess. Yeah, and next one is 6 plus the W3 square is 0.5. So 0.5 square, the 500 minus 30. So it is 0.5 square. What is the problem? I don't know. Just give me a minute. Okay, so 0.5 square into what was the size 500 minus that size 30 divided by ni into si, so that is 500 multiplied by 30, and here we will multiply by s3 square, so that is 6. Okay, and we'll add these terms. So it is here, it is okay. So here it will be, so you can calculate and we can find out the variance of this y bar st. Whenever here we have used this 30 because we are using the under equal allocation. Whenever we are using under so now here under proportional allocation, whenever we are using, then we will find out the variance of p y bar st. So that will here we will use this wi square will be same, only the change will be here in this 30 and here 30. So here the proportion was here 18, 27 and 45. So we'll write 18 here, 18 here. Okay, and the next one is 27. So 27 here and 25 here. Only the change will be that. Okay, so it will be like 0.2 square into 300 minus what was the n1p. So n1p was 18. So it is 18, 18, okay, divided by 300 into 18 multiplied by s1 square. So that is 3, I guess, 6. So that is 16. It is not 6, it is 36. It is 16 plus 0.3 square, 300 minus 27, I guess. So next one was 27, yes. Divided by 300 multiplied by 27. Okay, multiplied by, so the second one was 25. So SI square. So this is 25. Plus the next term 0.5 square, 300 minus 45 divided by 300 multiplied by 45 multiplied by 36. Again this expression we can calculate. Okay, now whenever we want to calculate the next one, so that is y bar st, whenever we are using the Neyman allocation, the optimum allocation. So under Neyman, so under optimum allocation, if I want to do, so we'll just change now to the sample sizes, which are this 14, 25 and 51 in place of this 14, 25. So here, okay, this is 27. Yeah, so it is 40, 25 and 14, 25 and 51. Okay, so then for that variance will be, variance of YRST will be what? So here it will be 0.2 square, 300 minus 14 divided by 300 into 14 multiplied by S1 square. So S1 square was, I guess, what was it? 16 plus 0.3 whole square, 300 minus 25 divided by 300 into 25 multiplied by, it was, I guess, 25 only. So the S2 square was, yeah, 25. Now it is 36. Next one is, so plus 0.5 whole square, 500 minus, the third sample size was 51. So it is 51 divided by 500 into 51. Okay, this is 14. 25 and 51, yeah, and multiplied by 36. Okay, so this is again calculated. So this will be the under the optimum allocation. So this way we can calculate the all three variances of the stratified sample mean. Okay, we are considering the underlying, the take, we are generating or taking the sample using the SRSWR. So that's why the SRSWR is playing role here when we are taking the variance of y bar st to be this. Okay, so this was about this question. However, in the next question, it is asked that the same question is asked actually, but in the question it is asked that what if when we are sampling by SRSWR. So whenever we are using SRSWR, then what is the variance of y bar stratified? So for that case, we have this variance I going from 1 to k, wi square ni minus 1 upon ni into ni multiplied by si square. Only difference is this term. Okay, the remaining things are same. We can again we can again find out the sample sizes using the all three techniques, the equal, proportional and Neyman location. Okay, for each of the technique, we will find out the variance of y bar st. Here we will put the values of the sample sizes for the different allocation techniques, and we will find three variances for one for the equal proportion allocation, sorry, equal allocation, second is for proportional allocation, third for the Neyman allocation. Only you need to put the values of ni according to the allocation method. I hope this is the same as the previous one, only this formula is changing. Apart from this, NIs will be calculated using these values NH and SH, NI and SI square. So I hope this you can do. Okay, so just do it yourself, because the whole idea is same, only this formula is changing. Okay. Is it fine? These two questions are same only. Is this question fine? Question 6 is fine. If question 6 is fine, then question 7 you can do. Okay, so is it fine? Then I'll move forward for the next one. Is there any doubt?
No doubt.
Okay. So then we'll move for the next one. So here the question is saying that let S to be equals to 2457 be the original sample. So this is the sample, okay, we have. Then which of the following are valid bootstrap samples? So first bootstrap sample is, and the A part, it is 2457, which is same, which is as it is. So this is valid, because what is important that the sample which we are taking from it, it should be taken from these values only, and the sample should be of size this size only. If S is of size 4, then we should also take the sample of size 4 only. Okay, this is due to the bootstrap technique. So we have a sample of size small n, then we will resample it again. We are not decreasing its size, we are resampling it again. Okay, so the first one is valid bootstrap sample. The second one, we are getting 2222. So is it a valid sample? Is it a valid sample which can be drawn from valid bootstrap sample? So basically, when we are drawing a bootstrap sample, the with replacement thing is allowed. So we can use the simple random sorry, the simple random sampling with replacement. Okay, so this 2222 is also valid. Okay. However, in the third part, we have the sample, the bootstrap sample whose size is 3. However, the size is 4 for the original sample. So this is not a valid sample. Why? Because of its size. Okay, because it is of size 3 and this is of size 4. So whenever we are taking a bootstrap sample, it should be of size 4 only if we are taking it from the size 4 original sample. Okay, so this is not correct. This is not valid. And the next one is 2467. So here 2 is there, 4 is there, but 6 which is there in the sample, it is not in the original sample. So here again, it is not a valid sample. Since 6 does not belongs to S, the original sample. Okay, that's why this is also not a valid sample. Now the fifth one is 5577. So 5 is there, 7 is there, and the length is also 4. So this is also a valid sample. Is it fine? So the thing is that the sample should be, the size of the sample which we are taking should be same as the size of the original sample, and the values are coming from it only. It should not be like that the value is not present in the sample and you are taking another value like this of part D. So this should not happen. This is not a valid bootstrap sample. I hope this is clear. So this was a kind
Yes,
of,
ma'am.
yeah. Okay, so we'll move for the next question. So let the observed sample be 246. Okay, four bootstrap samples are generated. So this B1 bootstrap sample, B2, B3, B4, four bootstrap samples are generated from this original sample. Okay, now find the bootstrap estimate of coefficient of variation. Okay, so what coefficient of variation is? So coefficient of variation is the standard deviation divided by mean. Okay, now for this data we do not have the standard deviation, we do not have the mean, but we can have the estimates for them. So since we have this sample, so from that sample we can here, in place of standard deviation we can write standard error, and in place of mean we can write the average. Okay, the sample mean, average, or I can say the sample mean. Fine. So what it is asking, that find the bootstrap estimate of coefficient of variation. So for each of this we should find the coefficient of variation first. Okay, so we will find out CV1 hat, we'll find out CV2 hat, we'll find out CV3 hat, we'll find out CV4 hat. Okay, so okay, I will use a little bit of R because we have to do the calculation. So let me do that. So here CV1 hat will be what? So we are doing the A part. So CV1 hat will be, so in R we can we have to find out the standard error divided by the sample mean. So we will write VAR of this vector, whatever this is, 224. Okay, 224 divided by mean of 224. Okay. Similarly, CV2 hat we can find out. Similarly, CV3 hat and CV4 hat. Okay. So let me write this in R. Okay. So here this question is ninth. So this is ninth question we are talking about. Okay. So I'm writing here for this CV1. So I'm naming it as CV1. Okay. And this is what? VAR of what? The first one is 224. 2 comma 2 comma 4. This is the first sample. Okay. VAR of this divided by mean of it. So this is mean of 2 comma 2 comma 4. So this will be the CV1. So what the CV1 is now? Okay, I should write it in C form now. So it is coming out to be 0.5. So it is 0.5. Similarly, I'll do for the second one. So the sample here is 466. Okay, so here it is 466. So I'll just copy it. So here it is 4, 6, 6. 6, 6. Okay, so it will be 0.25. So it is coming out to be 0.25. Okay, now similarly for CV3, So this is 246. So this is coming out to be 1. Okay. Then CV4 will, this is 666. This is coming out to be 0. Okay, so now we found out these values. So okay, this value we have found out. I want to find out the bootstrap estimate. So that bootstrap estimate for CV. So bootstrap estimate for CV will be mean of CV1 hat, CV2 hat, CV3 hat, and CV4 hat. Okay, we'll take the mean of all these quantities. So that will be the bootstrap estimate for the coefficient of variation. Okay, so I'll just take the mean here. So the mean of CV1, CV2, CV3, CV4, and I should store it as a vector. This one. Yes, okay, so this will be the bootstrap estimate. So I will just name it as bootstrap estimate. So it will be this. So it is coming out to be 0.4375. Okay, so that is, so I will just take it as a CV hat. So CV hat will be 0.4375. Fine. Now in the next question, it is asked that what is the bootstrap bias? So bootstrap bias they are talking about. So bootstrap bias will be the difference between this. Okay, I will call it as CV bar hat. Okay, so it will be the so bias will be CV bar hat. So it will be CV bar hat. Okay, minus CV hat. Now what this CV hat? So this we will take from the original sample. Okay, so it will be the coefficient of variation of the original sample. What was the original sample? The original sample was 246. Okay, so 246 and this sample is same only, so it will come out to be the same. So what will be the CV hat, which is basically this CV3 hat, which is basically 1. So CV hat is 1. Okay, so it is basically the variance of 246. So basically it is the original sample. That's why the variance, not variance, the standard or error of this. Okay, I have done a thing wrong actually. So it is the standard error divided by the mean. So here I should write the square root also, because the standard error is the square root of the variance. Okay, so I should write that also. Then these values will get changed actually. Okay, so then I'll just run it. So now I got CV1 to be 0.433 actually. So it is 0.433, 0.216, and 0.5 and 0. So it is 0.5 and this is 0. Okay, and CV hat is CV bar hat. So that is the mean. So that is coming out to be 0.287. Okay, so this is 0.287. Okay, now this is equal, so this CV hat will be standard error of 246 divided by mean of 246. So that is this CV3. So the CV3 is 0.5. So it is 0.5 here. Fine. So the bias will be the difference. So this is the difference, this 0.287, which we have found out, 0.287 minus 0.5. Okay, so this is, so the bias is 0.287 minus 0.5. This is minus 0.213. Okay, so basically it is underestimating it. The estimate is quite bigger, but the bootstrap estimate is a little lower. So that's why we are getting answer in negatives. So that is the bootstrap bias. Now the next question is compute the bootstrap standard error. So the bootstrap standard error will be the standard error of these values. Okay, so that will directly by the command we can find out. So that will be the variance of the square root of variance of the square root of variance of CV1 hat, CV2 hat, CV3 hat, and CV4 hat. Okay, so this will give us the bootstrap standard error. So let us find out that also. So the I will write it as a standard SE of bootstrap standard error. So PSE I will write it. So this is the SQRT of variance of C of CV1. I'll just copy and paste. Okay, so this will be this quantity BSE. So it is 0.2265. So it is 0.2265. Okay, if there is some mistake, the idea is this only. If there is some mistake, then just cross check it. So basically what we are doing, we are just finding out the coefficient of variation for each of the sample. Okay, then we will find out the mean. So the mean will be the bootstrap estimate of the coefficient of variation. Then we will subtract it from the coefficient of variation of the original sample. Then that will be the bias. Okay, and if we find out the standard error of these four uh, the bootstrap, so for particular sample there is a coefficient of variation, and if we find out the standard error of those coefficient of variations for different samples, then that will be the square root of that will be the standard error of the coefficient of variation, the bootstrap standard error. Okay, so is it fine? Is this fine question?
Yes, ma'am.
Okay. So now this is the last question. So this basically is on empirical distribution. So if I have a sample, then how to basically find out the empirical distribution in order to estimate the CDF. Okay. Now if I want to estimate F6, so what basically F6 means? This is probability X less than is equals to 6. Okay. So this is probability X less than is equals to 6. I want to find out using this sample. Okay, using empirical distribution of this sample, I want to find out that what can be an estimate for F6. So that is probability X less than equals to 6. So here basically this is the sample, and for each sample we are basically giving the equal probability to each of the values. We have 5 values, so we'll give probability 1 by 5 to each. So 1 by 5 to 3, 1 by 5 to 5, 1 by 5 to 6, 1 by 5 to 8, and 1 by 5 to 10. So we'll give equal probability. So what does it mean? That probability X is equals to 3 is 1 by 5. Probability X is equals to 5 is 1 by 5. Probability X is equals to 6 is 1 by 5. And probability X is equals to 8 is 1 by 5. And probability X is equals to 10 is again 1 by 5. So these are the distribution of the probability. Now apart from this, if there is something, okay, then it will have probability 0. Fine. Now I want probability this F6. I want to estimate this F6. So that is probability x less than or equals to 6. Okay. So it can be probability. So what are, so other than these numbers, the probability is 0. So we cannot, we do not consider them. We only consider the values which are present in the sample. So which are less than 6, less than or equals to 6? So that is 3, 5 and 6 only. So probability x is equals to 3 plus probability x is equals to 5 plus probability x is equals to 6. So that is 1 by 5 plus 1 by 5 plus 1 by 5. So that will be 3 by 5. Fine. Similarly, if I want F9, so that is probability x less than or equals to 9. Okay. So that is equals to, so what are this? 3, 5, 6, 8. 10 is greater than. So apart from this, they are all less than 5, 9. So, so that is probability x is equals to 3 plus probability x is equals to 5 plus probability x is equals to, apart from 5, 6 and 8. 6 plus probability x is equals to 8. Each one of them have 1 by 5 probability. So this will be 4 by 5. Okay. And again, we again want to, if I want to estimate this probability x greater than 5, so these are the estimates of this. Okay, this is not the exactly, we are just estimating this f6 from the empirical distribution. Now, what is probability x greater than 5? So that is probability x. So what are the values for which x greater than 5? So x is 6, 8 and 10. So probability x is equals to 6 plus probability x is equals to 8 plus probability x is equals to 10. So which will be 3 by 5. Okay. So this is the way by which we can estimate the distribution of the population through the empirical distribution when the sample is given. So on the basis of that sample, we are giving equal probabilities to the value present in the sample, and otherwise the probabilities are 0. Okay. So I think this is all for today. And uh, if you have any doubt, then you may ask regarding anything regarding this question or another thing. And we will now the recording I will be uploading on YouTube, and the presentation and the R script I will add on Google Drive. And I think the deadline of the assignment is 11th of March, and the next session will be on 16th March. Okay. So now if you have any doubt, then you can ask.
No doubt, ma'am.
Okay. So okay. So if I hope the things are clear, I've tried to include almost everything in
Yes.
the yeah. So okay, then if there are no doubts, then we'll meet in the next session. And
Okay.
yeah, thank you for your patience for waiting for 2 hours for this class. So yeah, okay then, you may leave, and
Thank
thank you for joining.